All right, we want to take a look at the Doppler effect. Some of you may be familiar with this, but everyone kind of knows what happens. Let's think about a car approaching you. You can talk about its engine or any sound coming off the car. This person happens to be beeping their horn, and they're traveling towards the observer at a very rapid speed. And then you'll notice as they go by, you hear that shift in pitch. It goes from high to low the second that they pass you. This is the idea behind the Doppler effect, is you have a sound that is moving, or the source of the sound is moving. So what ends up happening is that things get a little weird. We'll change the car horn to maybe a police siren because it happens with police cars too. It'll happen with any moving vehicle. What's weird about this is that this person right here is going to hear something different than this person right here simultaneously at the same time. And then once it passes, you get that high to low shift. And all that happens because the sound source itself is moving. So if you think about our representation of a wave from a stationary sound source, a sound wave, it radiated out in all directions. And that's what you see right here. And if you notice these crests, they're equally spaced. So what ends up happening is that this observer, anyone maybe up here, maybe someone down here, maybe someone here, they're all going to hear the same pitch. It's not going to be any different for anybody. They may hear different volumes because the intensity might be different, but they're not going to hear any of these weird effects. Once you have a moving sound source, what happens is that the source, each time it emits a new wave, is doing it from a different location. So what ends up happening is that the resulting pattern of the wave crest is going to be a little bit different. The person that's standing in front of here, you may notice that those crests are closer together. That's going to correspond to a higher frequency or a higher pitch. And then someone behind, they're going to be in a region where the crests are farther apart. So they're in a region of low pitch here. And this is the whole idea behind the Doppler effect. Now the equation for the Doppler effect can be a little bit wacky when initially looking at it. This is the frequency we hear. F0 is the true frequency. This is our speed of sound. We'll make it 343. And then this effect can happen if the source is moving. This effect can happen if the listener is moving. And so we have these plus or minuses based on all these scenarios. We'll take a look at it. Turns out that if the receiver, the listener, is moving towards the source, we're going to make VR positive. But if they're moving away, we'll make it negative. And then for the sound source itself, it's positive if moving away, negative if moving towards. So let's go through just an example to try to make sense of this. What we'll do is we'll take a person that is not moving. And if you took a look at that video, I believe the speed limit was 50 miles per hour on that road. So that would give us a good representation of, what kind of numbers we're looking to use. If I had to guess the pitch, and I'm not a perfect guess of pitch, I would guess that it was a 600 hertz siren. So here's our car, our 600 hertz horn. It's moving. We'll give it a 30 meter per second, which is, on the order of about 50 or 60 miles per hour. And it's traveling that way. There's its horn frequency. This is what the driver inside would hear. This is what the horn would sound like if you're still, or if the car is still. And here's our observer right now. So they're in that high frequency region. They're not moving. They're the listener, 0 meters per second. So using that formula, it's going to be pretty simple. You got your velocity of sound here, speed of sound. That's going to be 343 at all times. And then our receiver is not even moving. So that's going to be a +0. And then we've got the velocity of our source here. So let's put in our numbers, see what we end up getting. We get 600, 343 +0, 343. And actually the source is moving towards, so we want to make that negative, minus the 30 meters per second that they're traveling. So get some numbers here. This is pretty easy to solve. 600 times 343 divided by 343 minus 30, which is like 313. So this is what we get for the frequency that we hear. 657.5 hertz. So you hear a higher pitch while that is occurring. Now, if the person is over here and the car has passed them, now they're on the other side of that. The car is still moving 30 meters per second. But now, what we're going to do is change one thing here. The person is still at rest, so that's still 0. 343, you can't even see any of that. Now the car is moving away. The source is moving away. So if you looked at those rules, we now have to make this positive, and that would be plus 30. So it's going to be 600 times 343 divided by 373. What we're going to get is that the frequency we hear is about 551.7 hertz now. So you hear an even lower frequency as it passes you by. Now this effect can be magnified. If the car happens to be moving towards another car, we'll do the scenario where maybe the listener is moving as well. So here's our horn, 600 hertz, and they're moving at 30 meters per second. Let's have this car here move at 25 meters per second. This is the listener right here. So this is an entirely different scenario, and you're going to get a different result here. So essentially, we have to look at our rules. Our true frequency is 600 hertz. The speed of sound is still 343. Now the listener is moving, and the listener is moving toward the source. So if you look at the rules, we have to make that positive. That's going to be a plus 25 up there. And the car, the source, is moving toward the listener. So that's going to be negative. Minus 30. So let's look at those numbers. So we got 343 plus 25. And then in our area we have 343 minus 30. And if you take a look at the frequency, now we get 705 hertz. 705.4 hertz. Even larger than the very first scenario that we saw. So this effect is magnified by the fact that the listener is moving. And then once they pass each other, what's going to end up happening is that now the listener is moving away and the source is moving away. So looking at the rules, two things change here. Now you have to make this negative, and now you have to make the bottom part positive. So if we do that, what we're going to end up getting is a very low frequency relative to what we've seen, 511.5 hertz. So the effect is magnified in both cases because the listener is moving. So that's how the Doppler effect works. What we'll do next, we'll just take a look at a couple unique scenarios involving supersonic jets.